Welcome Math 212 students. We're going to be looking at Chapter 10, Section 2 today. In looking at this, we're going to be looking at line symmetry, and you'll be discussing this with your fourth grader. These are the different topics that we'll discuss in Section 10.2. First up, symmetry is in all sorts of different things that we look at. It's a very pleasing kind of shape for us to look at, very pleasing to the eye. Tessellations are like super cool. We love looking at tessellations. So let's look at our figures here, and each of these is well known, and each has a type of symmetry that we can look at. I look at this Canadian flag and see that I could draw a line straight through the middle here, fold that over, and I would have the other half. Same thing with the butterfly, and same thing with this snowflake here. With the Chinese yin-yang, you can see that each one fits inside the other of that shape. So what do we mean by the term symmetry? We're going to be looking at translation, reflection, rotation, and glide reflection. So what symmetry basically is a transformation that places the object directly on top of itself, kind of like a cut and paste is what I like to say to my students. It has reflection symmetry if we can draw a line and we can look at that, draw that line like we did with the Canadian flag, or like we did with the snowflake, and then we can fold it over and we can see the other side right on top of the other. It has rotation symmetry if we can draw that figure and then pick it up and then trace it and turn around and have the other one. That would be like the Chinese yin-yang figure that we looked at. So let's look at those again. There they are. We can say that the Chinese yin-yang has that rotation symmetry. Now some people think of rotation symmetry in terms of how much we have to turn it in order for it to lie back on top of itself. So let's imagine an equilateral triangle. Here they go through the verbiage of turning it a third of a turn. I think it's better to just look at the picture. For me it helps looking at the picture, and then we'll go back and look at the other slide. If I label the corners and I turn it a third of a turn, then I have the one down here, turn it a third again, and if I turn it one more time, I have my original figure back. Each time as I draw it, it is its same shape sitting on top of itself. So we would say that this figure, because it takes 3 rotation to get back to its original, has 120 degree rotation symmetry. And here we see that each time that we rotate this figure, it does fit on top of itself again. So let me get my pen here and we'll look at the different types of symmetry that we have here. I could see that this has that reflection symmetry right there, because if I draw that straight line, there he is. I can also, I don't see a way to rotate him and have him back on top of himself. This guy right here, if I rotate him 180 degrees, meaning if I rotate him, just turned him over, I would see that he would be sitting back on top of himself. So I don't see a way to draw a line and get this one back, because if I fold this over, his corner would be down there somewhere. This one, because it is more of a square rhombus that's been tilted, does have that line symmetry. It also has the 180 degree symmetry, because I could rotate it around 180 degrees, and 180 degrees, if you'll remember, is this much, so I could rotate it all the way around that way. For this rectangle, his line or reflection symmetry is, I could fold him over about either of those two lines and I would have him back. He has 180 degree symmetry as well. This guy looks like I could, same as the rectangle, fold him like this. But I could also fold him about the diagonals because he is so symmetric on either side. So that square has a lot of different kinds of symmetry. So this asks us to look at reflection and rotation symmetry on some other figures. So let's do that. Alright, well, we've already discussed that equilateral triangle, where did my pen go, that has a 120-degree rotation. We don't really have a line where we could, oh, wait a second, let's see. Could I draw it through? Oh, yeah, we do. I could draw it through there, fold it in half, or I could draw it through there. Okay, so that does have some reflection symmetry. We've already done the square, said that he had, oh, you know what he has? Let's look at that. I think I wrote 180, but he has 180, but he also has 90-degree symmetry. So he has both 90 and 180 because, of course, all I have to do is turn it twice to be the 90-degree symmetry. Nice. So if we look at the square, we've already done him. Let's see. I could have this line of symmetry. Looks like I could do it through every one of those corner points. And okay. And then as far as the rotational symmetry, let's see, that would be, I would rotate that. That has 1, 2, 3, 4, 5 sides. If I rotate it, whatever 360 divided by 5 is, that would be that type of rotational symmetry. This guy has symmetry. Could fold that in half. Could fold this in half. Wow. Could fold it in half here. Ooh, could fold it in half here. This guy has a lot of symmetry, doesn't he? And could fold it in a half here. And then since he has 6 sides, 360 divided by 6 would get me, so that would be 60-degree symmetry. There's 6 sides, right? 1, 2, yep, okay. And so you would carry on with the rest of them. I'll just leave those for you to do. We're looking at some letters of the alphabet, and we're trying to decide which one, if we cut them in half, like if I cut this A in half right here, that means I have the vertical line symmetry. Who else? You know, ooh, H. Cut the H in half. What about the I? Yeah, because he is kind of just that straight guy there. M. So those are called vertical line symmetry, and I could carry on with the rest of them. See that V, he has the vertical line, the W. Who has horizontal line reflection? Let me put the eraser on that puppy. Let's do some eraser. And then we'll do the horizontal. Oops, I don't want laser pointer. Pen. Who can I guess it depends on how you draw your B, but I could flip that up and back and that would be horizontal. Depending on how you draw your D, you know, you could have, as long as you draw it very symmetric, you could flip that back and forth. The same with the E, not the F. Oh, you could do it with the H. He has both. You could do it with the O. And carrying on. Ooh, you could probably do it necessarily with the K there. Alright, and then carrying on. I didn't do them all, but that gives you the general idea. And we do find patterns on quilts, ceilings, walls, floors, you know, our linoleum, tile work. How would we describe what happened here? We take this one general shape and we move it to the left, and then we draw that same shape down. How are we sliding it? How are we doing this glide translation? Here's some patterns here. These are tessellations, where you just draw one shape and then you draw that same shape again and it fits inside of itself. Very cool. Escher is an artist that did quite a bit of this. We'll look at that at the end of this. So In this, we're talking about translation symmetry. If we can lift the pattern, translate it some distance and in some direction, and then set it down on top of itself. It's reflection symmetry if we can draw a line and have it reflected back on top of itself. It has rotation symmetry if we can turn it and that pattern will fit on top of itself. It has glide reflection symmetry if we can find a translation in a line and we move it and follow it in that pattern in some direction. So let's look at these different strip patterns that we have here as an example. In A, what we have is just a pattern that is just sliding along, and this one would be called a translation vector. Now the B part is pretty fun, because if you were to draw a line straight through here, notice you could just flip it over and the pattern would repeat to here. So we could say that this was a pattern in threes. Or you could say that I just took this pattern of twos and moved it in this vector translation way. Either way, you would still be making that type of pattern. So our patterns don't necessarily just have one answer. Sometimes they have more than one or two or three, even three answers. In fact, you could say that I have a mirror line right here, because if I drew that line, folded it over, you would see I would have a pattern of 4. And likewise, you could do that in this section here and then say that you folded it over. So it continues on. Let's look at this C pattern. Now in this C pattern, I've got a double row. Notice I could say that I have a mirror line all the way across here. That's one way to say that we could create this pattern. Or you could say that I took this grouping and moved it along this translation line here and just made a bunch of them that way. Either way, I've made that set of shapes. If you'll look at D, another mirror pattern here, or I could even put a mirror line here, or you could say I took this group of 4 and just translated it that way. Now each one of the strips that we looked at had translation symmetry, so we're looking for other kinds of symmetry as well, just to see what other kinds of patterns that develop. Another kind of planar pattern is in wallpapers, just patterns that just repeat themselves. Those are always fun to look at. Brick patterns, how do we make these bricks? Are they translations? Are they reflections? You can see it's a combination of the two. I could look at this B part as this grouping and say that I was reflecting it down this way. That's one way to look at it. Symmetry breaking is also something that we like to look at. Symmetry breaking occurs when we take a pattern that has lots of symmetry and then we reduce the symmetry. Let's look at what we're talking about. Look at quilt patterns. Look at that A picture and how beautiful he is. He has all different kinds of lines of symmetry, reflection symmetry. If we put some colors in there, we now have no lines of symmetry. If we change the colors up, we can get different kinds of symmetry, such as the quarter turn symmetry, and then we might be able to see if we can have a folding symmetry as we look at those and see where those lines might be. Symmetry is expected in a lot of the things that we look at in our floors, in our walls, and we're looking for that because it makes us feel comfortable. It pleases the eye. So there are three-dimensional symmetry figures. If we look at the Taj Mahal, the U.S. Capitol building, forks, nuts, bolts, windows, they all have a type of symmetry. We also have naturally occurring objects or things that have symmetry, such as starfish, honeycombs, crystals. Love to look at those. So let's look at our three-dimensional symmetry. If we look at those and think about rotating those about a line or a plane. And we would look at those as rotating about a plane of symmetry. You just imagine a piece of paper and it was rotated about that. So if there's a line that can be drawn around which a three figure can be rotated, it has rotation symmetry. And then we would find its axis of symmetry. So here's a couple of three-dimensional objects, and we need to decide which of these has rotation or reflection symmetry. So let's look at a couple of lines of symmetry about this prism. If I take this prism and rotate it about this line, you can see that I would have the same thing either way. I also have this vertical line of symmetry where I can rotate it and get that same figure back. With the nightstand, that would be right in here. I would be able to look at both the left and right sides and see that it reflects back on each other. Alright, and here we are looking at those two. They're describing that for us. Yep, we've been looking at some transformational geometry and we've been looking at some patterns, and now we're going to look at tessellations. Tessellations are fun to look at and fun to color. And you can find all sorts of coloring books and talk about tessellations with your students. Here are some tessellations where you make one shape and you keep repeating that shape and it just fits inside of itself. Don't concern yourself with the borders, and that's what this is telling you. Don't concern yourself with the borders. So fitting tiles, square, rectangular tiles on a floor, making that tessellation occur, making some pattern repeat itself over and over. Which of these triangles will tessellate and keep on creating a pattern? So you have to keep drawing that same triangle. You can flip it about, but as long as it fits on itself, and I could just keep on drawing these triangles and see it flipping about itself, and I could do one to the side and you could see that it would keep tessellating about itself. And this one right here would require a little more work, but what if I did, like, let's see, I'm probably not going to be able to draw. That's not going to be it. That one, it would require me to piddle with it just a little more to see if it would actually tessellate on the plane, because I would have to really draw it. So what I would do is just trace it to try to figure that one out. Here's some beautiful tessellations. I can see that I have this one basic shape. It is kind of like this house looking shape, and I just keep making that shape over and over again. You could see that, whoops, lovely, we're doing this. And I could just keep making them, and I would just fill up the space with this same shape. These arrows are really cool. Here are some Escher style tessellations. These are beautiful, very famous, and super cool to color and look at. And giving your students some sort of task or some sort of coloring opportunity or even drawing opportunity to do this is a lot of fun when you talk about tessellations. And that's all I have for section 2. If you guys have any questions, be sure and email me.